Hey class, how are we all doing? Yeah, I wanted to give you guys a short video to cover the rest of the concepts from chapter 6-2. We discussed much of the ideas in this chapter already in class yesterday, but I just wanted to give you another kind of taste of the whole round picture and hit on some of the ideas that we didn't fully unpack as we went through some of those questions yesterday. So there's four main things we're going to be discussing as we talk about how aerodynamics work around baseballs in particular. So we're going to talk about what types of forces a ball moving through the air will experience. Specifically, what is air resistance? Where does it come from? What gives rise to air resistance? With answering that, we're going to talk about how the ball moves through the air and really how the air flows around the ball, and then use that to explain how some balls are able to curve, and then also talk about why things like golf balls have dimples or tennis balls have this green fuzz, what purpose those things serve. So first of all, why do balls experience air resistance? Well, ultimately, it's because, as we talked about yesterday, the ball interacting with the air around it. So it's transferring its momentum. It's moving through the air, hitting air molecules that are in the way, and as it does, it transfers that momentum to the air. And part of the mechanism that occurs is as that's happening, as it's trying to push that air out of the way, as it's transferring momentum, pressure difference is created between the front and the back side of the ball, generating a net force pushing backwards on the ball. So you can kind of think about much of aerodynamics in sort of two ways. You can think about it in terms of transfer of momentum or conservation of momentum, which is directly related to Newton's third law of forces having equal and opposite forces. Or you can think of it also in terms of pressure differences that are generated as these mechanisms occur. So both in this section and when we start talking about flight, you can sort of conceptualize it as you think about transfer of momentum as well as about pressure differences that are being created. Both of those ideas give you a full picture of how we can explain how things move through the air. So when a ball is moving through the air, drag forces happen. So drag forces are another name for air resistance. And there's two types of drag force that we'll be talking about here in just a little bit. You can also have balls experiencing what we call lift forces. So those are forces, as I mentioned yesterday, that are perpendicular to the direction of motion. So if we say my ball is moving this direction, drag forces are going to be backwards against the direction of motion, and lift forces are going to be perpendicular to the direction of motion to cause it to curve up or down or left or right. So in baseball, you can throw a curveball that it can kind of go left or right, sometimes a sinker which goes down, and then in softball, because of the different mechanism of how you pitch, you can actually put backspin and cause it to spin upward as well, which is a really neat pitch to throw, but a very hard one, I think, for people to hit. So again, the drag forces, as you can see in this picture, are going back towards the pitcher against the direction of motion of the ball, and then lift forces based on the spin are going to be more or less perpendicular to the direction of motion, up, down, left, or right. So again, if the ball in this picture is moving to the left as we look at it, drag would be to the right, and lift could be up, down, left, or right. So again, as I mentioned earlier, with drag, there's actually two types. One is like friction with the air. So as the ball is moving through the air, it's rubbing against the air in a sense, and so that's oftentimes called skin friction or viscous drag. So viscous forces, if you recall, right, are about friction within fluids. And so this is friction between the ball and a fluid, the air, and that gives rise or generates viscous drag. All right, now the drag caused by a different pressure in front and behind the ball is what we call pressure drag. And so as we'll unpack here in just a few minutes, if a ball is moving very slowly, the air moves around so smoothly that there's almost no pressure difference, and so there's almost no pressure drag. But if you have turbulence behind your ball, if you have chaotic flow behind your ball, then that will generate a region of lower pressure than you have in the front of the ball, and that pressure difference generates pressure drag. So I have some pictures to help you visualize these ideas going forward, but I just want to unpack it. So air resistance is also known as drag forces. There's another name for drag forces, and drag forces can be broken up into two types: viscous drag, which is friction with the air, and pressure drag, which is generated by a pressure difference on either side of your ball. Okay, and then when you're deflecting or pushing air up, down, left, or right, as you deflect the air, it will also deflect the ball in the opposite direction, again, conservation of momentum. And so these forces that are perpendicular to your direction of motion, we call lift forces. All right, so let's unpack this a little bit more and see how air flows around a ball to understand what type of drag we have. And then as we continue into the next question, how we can generate curve with our ball as well. So ultimately, right, how the air flows, it's either going to be laminar or turbulent based on the Reynolds number, right? So if you have a lower Reynolds number, again, as we mentioned, below around 2,300, then you're going to have laminar flow. And if you have a higher Reynolds number, then you're going to have turbulent flow. And so if you have laminar flow, again, you have smooth flow over the ball, all you'll have is friction with the air, much less overall drag force. As your Reynolds number increases, as your object starts to move faster, turbulence will ensue behind your object, and you will get pressure differences, which generate pressure drag, which ends up being a lot more. So like something I've done to kind of visualize this idea or think about it, if you ever take something, kind of big and lightweight, like a balloon or something, and if you toss it very gently and see how far it goes, take that same balloon and throw it as hard as you can and see how far it goes. They almost go the same exact distance, because when you throw it much harder, there's much more turbulent flow behind the ball because it's moving faster, generating a higher Reynolds number, and it gets more drag force. And so even though you tried to give it more initial velocity, it had so much more air resistance, so many more newtons of drag force, that it ended up not going hardly any further than when you barely tossed it. So here's a visualization of what it looks like for a ball to be experiencing just laminar flow. This ball would have to be moving through the air quite slowly to get this kind of flow. Just to understand these pictures, we're going to see a few of these as we go forward in this section and the next. But this is our baseball. It's moving to the left. So these arrows represent the direction of air moving around your ball. But in reality, in most cases, unless there's a lot of wind, the ball is really being thrown through the air to the left. But we're trying to just focus on the ball. So it's as if our camera is moving with the ball, and so the air appears to be going to the right. So as we talked about in class, right, as the air hits the front of the ball, the air will slow down. As speed goes down, pressure goes up. And so you end up with high pressure, low speed in front of the ball. On the sides now, as the air rushes around your ball, okay, it's going to move faster on those sides, and so therefore the speed goes up and the pressure goes down. And if your ball is moving slow enough through the air has time to rush around behind your ball, fill in behind the ball, and create another region of high pressure and low speed here behind the ball. So again, in front of the ball, your pressure is high, and your flow rate, the speed of the air, ends up being slower because it's hitting the front of the ball and slowing down relative to the ball. On the sides, the pressure drops because the air is rushing around the ball to try to fill in behind it. Okay, because it's being bent by the ball, it has a larger distance to cover, so it moves faster. The flow rate is up and the pressure is down. And then back behind the ball, again, the air rushes in, kind of slamming into each other from different sides, slowing back down and creating a higher pressure region. So again, if we have laminar flow, which is a big if, right? You have to have objects moving quite slowly. If you have laminar flow, then your pressure on the two sides of the ball are approximately equal and opposite, and and the pressure in front and behind the ball is approximately equal and opposite. And so the only net force you have is the drag force due to air resistance. All right, so you're going to have to remind me that, or explain to me that you understand this information on homework 16. So keep in mind, there's going to be some questions about this on homework 16. All right, so in this case, you only have one force. It's a viscous drag force pointing backwards. Now, eventually, if you throw the ball fast at all, any faster than a few meters per second, eventually it's going to move so fast that the air behind the ball back here, I almost pointed to my screen, you guys can't see that. The air behind the ball back here won't have time to rush in and fill in a nice, smooth, laminar manner as we see here. So if the ball starts moving faster, as the air tries to rush in back behind the ball, turbulence will be generated. All right, so what happens is you now get this chaotic flow. Now these lines, because they'd be going in all different directions, the turbulent wake is just going to be shown as like a broad blue spot without any smooth lines, because there's no streamlines since everything's moving chaotically. But eventually the air can no longer rush in behind the ball, and so eventually they say it kind of detaches off the ball and starts tumbling around. And so you generate a large area of turbulence behind the ball, which we call a turbulent wake, the wake of the airflow behind the ball. So you get this big wake back behind the ball, and where that wake is a region of lower pressure because the air is moving all chaotically around. It's not pushing uniformly against the ball. And so what happens now is we have high pressure in front and lower pressure behind, and so you generate pressure drag. And the air is still rubbing against the front of the ball, so viscous drag is still present, but now you also have pressure drag, which is usually much stronger than just the viscous drag, and so you end up with a larger overall net air resistance, net drag force pushing against the ball. So when things are moving faster, they experience more air resistance, which we see in day-to-day life and understanding, like with cars especially. I drive an electric vehicle. It's most efficient at like 20 to 25 miles an hour. Once I get going faster, the air resistance is so strong that I really lose efficiency in my battery power. All right, so that's understanding drag. Hopefully, again, you understand, right? We are just looking at balls being thrown straight through the air. Once they get going very fast, you get a turbulent wake behind the ball that generates pressure drag. And we're going to talk at the end of this section, how do we reduce that drag? But for now, I want to continue to look at airflow around the ball first. So to cause a ball to curve in flight, to generate curvature, you need to generate some sort of lift force. All right, there's two main lift forces that we're going to discuss and understand. One is what's known as the Magnus force, which we briefly introduced yesterday. And the second is what's known as the wake deflection force. And they both work in very similar ways, but the Magnus force is the laminar effect. And so the way in which you create smooth flow on top of your ball and smooth flow on the bottom of the ball that are different, generating a pressure difference based on the speeds of the flow, and that will generate a Magnus force. But there's also, if you have turbulence behind your ball, if you're able to cause that turbulent wake to be off at an angle, that generates a net force also that can generate lift or cause your ball to curve in addition. So you can have, again, pressure differences caused by the rotation, and you can have a deflected wake, which also can add to your lift force. So let's just look at just the Magnus force. So let's assume for now that there's no wake. Now it's not a great assumption, but that will help us understand just the Magnus force, and then we'll add the wake here in a second. So if your ball's spinning, again, let's imagine this is a top-down view, all right? The ball's moving to our left, and it's rotating in a clockwise manner. So again, up at the top of the ball, up here, right, the ball is moving with the direction that the air is flowing up at the top, and so it's kind of, because of the friction, because of viscosity and viscous forces, it's able to pull the air around the surface of the ball, keeping it in contact with the ball longer up at the top. And so you get this long path. So since that air is going a greater distance, its velocity will be higher, creating a lower pressure. Down at the bottom down here, on the other hand, all right, down here, the ball is moving against the direction of motion, slowing down the airflow, causing the velocity to go down, the flow rate to go down, and therefore the pressure to increase. All right, so you're creating this pressure imbalance by using the rotation of the ball, and that pressure imbalance generates a net force from the high pressure to the low pressure, which causes your ball to curve. And as you can see, the overall flow of air around the ball is deflected as well. So you can think of this also as being the ball sort of pushing off the air. If it pushes the air, in this case, sort of down, right, then the ball will be pushed sort of up. And so you can see that's what's happening as the ball gets pushed, or excuse me, as the curvature, the rotation of the ball pushes the air down, the ball gets pushed upward, and we call that the Magnus force. Again, down here is where we have the slower speed with the high pressure. Up here is where we have the higher speed with the low pressure, generating a net force upward that we call the Magnus force. Okay, so here again, we have the rotation of the ball. Now, if you have turbulence generated behind your ball, back here, you'll have a wake that's off at an angle. And so this wake, now being at an angle, again, high pressure in front, low pressure back behind the ball, can generate a wake deflection force. Again, pushing from high to low will end up kind of having a net force pushing your ball off. Again, there's going to be a great amount of this will be drag force. like air resistance, but a little bit of difference in the angle of these two can add to the curvature of the ball. So the asymmetric wake, just like the asymmetric airflow, both generate forces kind of in the upward direction. Now, again, because the wake still has turbulent flow, it will still generate pressure drag, so there'll still be air resistance. So in this case, if you have a rotating ball like this with a wake, all four of these forces we're talking about will be present. There's still friction with the air, so there's still viscous drag. There's still a wake behind the ball, so there's still pressure drag. You have rotation deflecting the flow, so you still have Magnus force, and because you have a wake that's deflected offwards, you have the wake deflection force. So all four of those aerodynamic forces would be in effect on this type of situation. All right, so the last thing I want to talk about, just to wrap up this section here, is why do balls have dimples, or why do tennis balls have these little fuzzes on them, or even why do baseballs have seams, right? So for baseballs, part of the seam is for the person holding the ball to get better grip, to throw, to be able to do curve balls and so on. But like with a golf ball, the dimples don't do that. No one's like throwing curve balls with a golf ball, right? Sometimes I hit curve balls on accident when I slice it way off into the trees or lake or something. But the question is, what is the purpose of this? And it's really fascinating, okay? One of the favorite jokes people used to make, my wife and I had a Subaru that had hail damage. So it had these bumps all over it from hail damage. We had bought it out in Colorado shortly after a hailstorm. And all of our engineering friends and physics friends would always, regardless of who they were, seem to love making the same joke, asking us if our car got better gas mileage because the dimples on golf balls are supposed to reduce air resistance and allow them to fly further. And so they thought that the dimples on our car would enable our car to get better gas mileage by reducing air resistance. And maybe that was true. I didn't have a good way to do a controlled experiment since I couldn't just magically take away the dimples, do a test, and then add the dimples back. So I don't know for sure, but I hope it did. Anyway, so these dimples in theory are supposed to reduce air resistance. So the question is how? What does adding a bunch of dents on the top of your ball, how does that help your ball fly further? It's really quite weird. Well, what it does is it's in a sense, I like to think of it as sort of creating controlled chaos. It generates small scale turbulence that actually helps reduce the effect of the larger scale turbulence, which is really quite interesting. So it does what we call creating a turbulent boundary layer. Now this is a little confusing, okay, so we'll kind of unpack it together, but a boundary layer is the air very near the surface, all right, so the air right along the very edge of your ball. And so again, the boundary layer is the air right next to it, okay? If you have smooth flow going right over the edge, then that's what we call a laminar boundary layer. So it's really smooth, and it's actually like friction rolling along the surface. And then if your air is turbulent on the surface, then it's sort of tumbling along the surface, okay? So you can think of laminar boundary layer being air sort of rubbing along the surface, and a turbulent boundary layer as air sort of rolling along the surface. So you can start to think right there, turbulent boundary layer, it's like a little wheel rolling, reducing friction on the surface, whereas a laminar boundary layer is like rubbing, and that has more friction along the surface. So here's kind of pictures to visualize that. If we zoomed in really close on the surface of a ball, what you would see is if you had a laminar boundary layer, is you'd have smooth lines rubbing along the surface of your ball. The boundary layer is just kind of the little bit right next to the surface of your ball. So we're really zoomed in here. And then a turbulent boundary layer is one that's sort of tumbling along the surface, but it's only happening on a small scale right near the surface. As you get further away, it returns to smooth flow. Okay, so it's tumbling just on a very small scale near the surface. So this here is a laminar boundary layer. This is a turbulent boundary layer. And what happens is if you have a laminar boundary layer, that friction along the surface causes the air to get caught up on the surface of the ball, and it creates a wake, a turbulent wake that's really quite large behind the ball. If you have this turbulent boundary layer where it's sort of tumbling along the surface, it's able to stay along the surface longer because the friction isn't slowing it down as much. And so you're able to have a situation where the air is actually able to stay along the surface of the ball longer as it sort of rolls along the edge, and your wake, the size of that turbulent wake, is dramatically reduced. And so since you have a smaller turbulent wake, you get less pressure difference. So the incredible thing is here that you end up with a situation where you have not only less friction with the air, less viscous drag, but you also end up with a much smaller wake and therefore much less pressure drag. And that's where the big difference comes in. So if you're able to trip up your boundary layer on a small scale, you can reduce your overall drag significantly. And that's what those kind of hairs on a tennis ball do, as well as dimples on a golf ball. Okay, so again, whether we're talking about seams on a baseball, hairs on a tennis ball, or dimples on a golf ball or wiffle balls or other things, all of these trip up the boundary layer, generating a turbulent boundary layer which rolls across the surface, and just like a wheel, that reduces friction and ends up reducing the size of the wake as well. So that's, yeah, we're at about 20 minutes. That's probably long enough on this section and should give you enough information to really understand fully how balls move through the air. Next, we'll apply these same ideas to how airplanes are able to fly. So get excited for that. Talk to you later.